This content is produced by Pass the CSLB, an independent audio-first study companion for busy California B general candidates. I build these lessons from official CSLB study guide topics and reputable, source-backed California materials so you can study on the go. This is exam prep reinforcement, not legal, professional, engineering, or job-specific advice. Exam content is set by PSI and the CSLB and may change, so always verify current requirements against official CSLB materials. No exam outcome is guaranteed. Now let's get into it. The most important field decision in this topic is easy to miss. A pressure-reducing valve can solve excessive incoming pressure and, at the same time, create a closed condition that needs its own pressure control. I want you to remember the sequence, not just the parts. First, control excessive incoming pressure. Then ask whether expanded water can move backward toward the supply. If it cannot, coordinate approved thermal expansion control. That is the central supervision habit. A regulator is not the end of the pressure conversation. It changes the boundary of the system. Based on the published CSLB study outline, plumbing hazard recognition and field coordination fall within testable material. The general B responsibility here is to recognize the condition, coordinate the plumbing work, and verify the required protection without stepping into device sizing or hydraulic design. Static pressure is the pressure in the water supply while the water is at rest. Residual pressure is the pressure that remains while the system is delivering water after friction and elevation losses have taken their share. Those are different measurements, and mixing them up leads to bad decisions. The California Plumbing Code limit in this research is straightforward. Static water pressure inside the building. Water supply piping must not exceed 80 pounds per square inch. When the incoming static pressure exceeds 80 pounds per square inch, an approved pressure regulator is required. The research report states that an adequate strainer precedes the regulator, while also noting an exception for regulators 1 1/2 inches or larger. The strainer screens supply debris that could interfere with the regulator mechanism. For a general B contractor, the field question is not how to select the internal spring or calculate the valve size. The field question is whether the high pressure condition, approved regulator, applicable strainer requirement, inspection, and related expansion control were identified early enough to be included in the work. The lower boundary matters too. The system must provide at least 15 pounds per square inch of residual pressure at the fixtures after accounting for friction and elevation losses. That does not mean every fixture must read the same pressure at every moment. It means the design and installation must preserve the required residual pressure under the applicable operating condition. I put the pressure rules side by side because the distinction is worth seeing. 80 pounds per square inch is the maximum static pressure. 15 pounds per square inch is the minimum residual pressure at fixtures. Pressure above the static limit points toward an approved regulator and the applicable strainer rule. A system that blocks reverse movement also points toward approved thermal expansion control. Imagine a hypothetical track project at the base of a steep elevation change. The service pressure measures 115 pounds per square inch while no water is flowing. Treating that reading as a bonus would be a serious supervision mistake. The pressure exceeds the statewide static limit described in the research, so the contractor needs to coordinate the approved regulator and verify whether the strainer requirement applies to the selected regulator, rather than allowing that pressure to reach the building piping unchecked. I also want to separate pressure from flow. A strong static reading does not prove that useful pressure will remain when fixtures operate. Long runs, elevation gain, and friction can reduce residual pressure. That is why the maximum static number and the minimum residual number belong in the same mental picture, even though they describe opposite ends of the problem. Now follow the water past the regulator. If the completed arrangement prevents water from moving backward toward the public supply, the building has become a closed plumbing system. When the water heater raises the temperature, the water volume expands. In an open arrangement, some expanded volume may move back toward the supply. In a closed arrangement, that path is blocked. Water does not offer much compression space, so the expanding volume can drive pressure upward inside the building. The California Plumbing Code requirement identified in this research is an approved thermal expansion tank, or an equivalent pressure relief mechanism for the closed system. When an expansion tank is used, it is coordinated on the cold water distribution, piping downstream of the device that created the closed condition. I think of the regulator as a one-way security door and the expansion tank as a controlled room for the extra volume. The door addresses what enters. The extra room addresses what happens after the water is heated. The analogy is not a substitute for the plans or the plumbing code, but it helps preserve the correct cause and effect. A common confusion is to assume that the pressure regulator absorbs thermal expansion. It does not perform the expansion tank's job. The regulator controls incoming pressure. The expansion control accepts or relieves the pressure increase created when heated water cannot move backward. Those are separate functions, and the contractor needs to see both in the scope. Suppose a contractor recognizes the high service pressure and adds the regulator but overlooks the closed system consequence. The immediate result may be an inspection conflict if the required expansion control is missing. After operation begins, the trapped expansion can produce repeated pressure spikes and may contribute to relief valve discharge, accelerated wear, or leakage. The exact symptom depends on the system, so I would not diagnose from one symptom alone. I would verify the closed system condition and the approved expansion protection. This is also a sequencing issue. The pressure condition affects estimating before rough plumbing. The regulator affects the system boundary. The system boundary affects expansion control near the water heating equipment. One missed decision at the service can show up later in another part of the building. Pressure protection keeps the building piping within its operating limits. Backflow protection keeps the potable supply from reversing toward contamination. The two subjects connect because both depend on pressure direction and one-way control. Potable water is water approved for drinking. Non-potable water is not approved for drinking. A cross-connection is an actual or potential physical arrangement that connects the potable system to a non-potable system, sewer, drain, or other unapproved fluid source. The word potential matters. Contamination does not need to have happened yet for the arrangement to be a cross-connection hazard. Backflow is the unintended reversal of flow through that connection. I want you to remember two forces: backpressure pushes, backsiphonage pulls. Backpressure occurs when downstream pressure becomes greater than the upstream public supply pressure. A booster pump, elevated storage, or trapped thermal expansion can create the higher downstream force. The contaminated or non-potable fluid is then pushed toward the potable side. Backsiphonage begins with a drop in the supply pressure. A main break, a major firefighting draw, or another severe pressure loss can create a vacuum-like condition that pulls fluid backward. The downstream system does not need a powerful pump. The loss of pressure on the clean side supplies the pulling force. The comparison table reduces the distinction to the part that matters in the field. Backpressure is a push caused by higher downstream pressure. Backsiphonage is a pull caused by reduced supply pressure. Both can create backflow if a cross-connection exists, but the pressure event is different. Consider a hypothetical hose connected to temporary potable water and left submerged in a container of mortar mixing water. Under normal pressure, nothing may appear to be moving backward. If the supply pressure suddenly drops, the submerged hose becomes a possible path for backsiphonage. The safe supervision decision is to remove the cross-connection condition and coordinate approved backflow protection for the actual use. A closed faucet alone is not a reason to ignore the submerged outlet. Now change the scenario. Suppose a booster pump on the downstream side produces pressure greater than the public supply. That is not backsiphonage. The pump is pushing from the customer side, so the hydraulic condition is backpressure. The push and pull memory aid keeps the two mechanisms separate without oversimplifying the hazard. The cleanest physical separation is an air gap. An air gap is an unobstructed vertical distance through open atmosphere between the lowest opening of the discharge and the flood level rim of the receiving vessel. There is no submerged outlet and no continuous pipe path for contaminated liquid to travel backward through. For the drainage air gap rule in this research, the vertical separation must be at least twice the inner diameter of the discharge pipe, and it can never be less than 1 inch. Both parts matter. Calculate twice the inner diameter, then compare that result with the 1 inch minimum. The larger requirement controls. If the inner diameter is 1/2 inch, twice the diameter is 1 inch, so the required separation is at least 1 inch. If the inner diameter is 3/4 of an inch, twice the diameter is 1 1/2 inches, so the larger 1 1/2 inch distance controls. The mistake is to look at a visible space and decide that it feels adequate. The rule is measured from the correct points, and the flood level rim matters. A small gap below the rim or a discharge opening that can become submerged does not provide the same separation. An air gap has no springs, seals, or moving checks. Its protection comes from visible atmospheric separation. Mechanical backflow assemblies have legitimate applications, but device selection depends on the hazard, the approved design, the code, and the authority having jurisdiction. The general B boundary is to recognize the risk and coordinate the approved method, not to invent a device selection in the field. Alternate water systems make cross-connection control especially important because potable and non-potable piping can occupy the same building. Rainwater and graywater systems may serve approved non-potable uses, but color coding and visual inspection alone cannot prove that concealed piping was never connected incorrectly. The initial test described in the California Plumbing Code uses pressure to reveal a hidden connection. The potable water system is activated and pressurized. The alternate water system is shut down, fully depressurized, and drained. The non-potable fixtures and outlets are then observed. If water appears where the alternate system should be empty, the systems are not isolated as intended. The sequence table shows the logic. Pressurize the potable system, depressurize and drain the alternate system. Observe the alternate side for unexpected flow. Any flow requires investigation and correction before the system is accepted or activated. I treat this as a project coordination milestone, not a last-minute paperwork item. The plumbing subcontractor, the authority having jurisdiction, and the people responsible for the alternate water system need the correct system states and access to perform the test. The general B contractor needs to schedule that work before closeout pressure makes correction expensive. The test is a physical verification method. It does not depend on trusting pipe color, labels, or memory. By placing one system under pressure while the other is empty, the test forces a hidden connection to reveal itself through flow. That is the practical why. The code requires the test condition, and the physical result gives the inspection team evidence about whether the systems are separated. The same protection principle applies during construction, not only after the permanent plumbing is complete. California occupational safety and health regulations require employers to provide adequate, potable drinking water and protect the way that water is dispensed. Portable drinking water dispensers must be capable of being tightly closed and must have a tap. Dipping from the container is prohibited. An open barrel with a communal cup is not an acceptable substitute for a closed dispenser with controlled delivery. Non-potable job site water systems must also be arranged to prevent backsiphonage into the potable supply. That includes temporary uses that can create a cross-connection, such as hoses serving industrial processes, mixing operations, or other non-potable work. The exact approved protective device depends on the installation and applicable requirements, but the hazard recognition is direct. Do not let a potable outlet remain connected to a contaminated source in a way that can reverse flow. Imagine a hypothetical summer framing site. One hydration station uses a tightly closed, insulated dispenser with a tap. Another station uses an open container where workers dip cups. The second arrangement creates a sanitation problem, even if the water started clean. Now imagine a process hose lying below the surface of dirty water. A sudden supply pressure loss can turn that hose into a backsiphonage path. The permanent building and the temporary site are governed by the same basic discipline. Protect potable water from contact and reverse flow. I want to leave you with one connected memory line. 80 is the maximum static pressure. 15 is the minimum residual pressure at fixtures. Pressure above the static limit requires an approved regulator, and the strainer rule includes the size exception stated in the research. A closed system requires approved thermal expansion control. Back pressure pushes, backsiphonage pulls. An air gap is at least twice the inner diameter and never less than 1 inch. For the initial alternate water test, the potable side is pressurized while the alternate side is depressurized and drained. Job site drinking water stays in a tightly closed dispenser with a tap, and dipping is prohibited. The deeper lesson is that water supply protection is about boundaries. Pressure must stay within an upper and lower operating range. Heated water needs a safe place to expand when reverse movement is blocked. Potable water needs a physical or approved mechanical boundary from non-potable water. Testing confirms that concealed boundaries are real, and job site practices protect those boundaries before the building is finished. I made an audio practice quiz for this specific episode so you can check these pressure, backflow, air gap, and cross-connection decisions. It is audio-based. The questions are read aloud and you answer by tapping, so it works for people studying on the go. When you are driving, wait until you are safely stopped before tapping. Go to the description below this video. You will see a link that says, Pass the CSLB. Tap it. It will take you straight there. Comment below with any questions about anything I covered. I want to know which distinction still feels unclear so I can help you tighten it up. Subscribe to stay on track through every episode until you get your license.